it's a pleasure to be able to be here, and I enjoy having the opportunity to tell you about some of our recent work and the work of our collaborators. So I want to talk about novel electronic phases and competing interactions in this very interesting heavy fermion compound, uranium ruthenium-2 silicon-2, which has a long history. And let me just say that there's, this is an understatement, there's been an enormous amount of interest in this compound during the past 3 decades, and there are of the order of 1,000 papers written about this material. And in this material there's a delicate interplay between competing interactions, and this leads to a variety of correlated electron phases and phenomena. And of course the one that's attracted the most attention is the hidden order phase, whose order parameter has not yet been identified. A very interesting type of unconventional superconductivity, antiferromagnetism, ferromagnetism, heavy fermion behavior in the compound itself, quantum criticality and non-fermionic behavior, and quantum phases, and I'm sure other things as well. And these interactions can be tuned via chemical substituent composition, X, pressure P, and magnetic field. So this leads to complex temperature versus composition, pressure, and magnetic field phase diagrams, and I'll show you some of those, containing these various phases that I just mentioned. And of course, there's this quest to identify the order parameter of the hidden order phase. So we've been especially interested in recent years in uranium ruthenium-2 silicon-2 as a platform for studies of quantum phase transitions and criticality that again can be tuned via these control parameters that I mentioned. And for example, the application of magnetic field leads to the suppression of hidden order and the emergence of quantum phases at high magnetic field. I'll mention some of that work. Also, the substitution of rhenium for ruthenium suppresses hidden order, and then you find the emergence of ferromagnetism and an unusual type of non-fermionic behavior. And another example is the substitution of iron or osmium for ruthenium leads to a transition from the hidden order to the large moment antiferromagnetic phase with a twofold enhancement of the phase boundary that describes these two phases. And that's what I'm going to concentrate on today. And these are some nice reviews by Dash and Openier in Reviews of Modern Physics, and more recently in Philosophical Magazine. If you want to avoid reading those 1,000 papers, then you could start there. And it gives a good summary of this problem. Okay, so I want to talk about some examples of research on the system, iron substituted uranium ruthenium-2 silicon-2, that have been carried out in our lab at UCSD and in the labs of some of our collaborators. So this will be kind of a progress report, and I'll mention some of the work that's been done by collaborators, but there are other collaborators that are going to be giving talks here, and I'm not going to really mention that work, which they'll describe, I'm sure, in some detail. But anyway, these are the topics that I want to touch on. I may not get to everything, but let me just say that the experiments indicate that the substitution of iron for ruthenium is analogous to the application of pressure in driving this hidden order large moment antiferromagnetic phase transition in uranium ruthenium-2 silicon-2. And so the iron concentration is now a new control parameter that allows you to access and study the hidden order in large moment antiferromagnetic phases, and also the actual transition between these two phases. There's a reduction of the unit cell volume for the substitution of iron for ruthenium, which apparently acts as a chemical pressure, and also very important for the purposes of this conference is that this opens up the possibility of studying uranium ruthenium-2 silicon-2 hidden order in large moment antiferromagnetic phases at ambient pressure with experimental techniques that are difficult and maybe even impossible to employ high pressure, such as ARCAS, SDM, and inelastic neutron scattering, and so on. Of course, you'd want to do this with single crystals, and I'll mention some of that as we go on. I should mention that there's similar behavior occurs for osmium substitutions. iron reduces the unit cell volume, osmium actually expands it. So there's something we don't really understand about the mechanism for this. And so I'll mention that at some point, at a certain point. Okay, so the research that I'm going to discuss in this talk are crystal growth and the general properties and some pressure work that we carried out at UCSD, some thermal expansion work with an apparatus and some measurements that at quantum design, measurements also in our own lab, neutron diffraction at Los Alamos and NIST, elastic neutron scattering at NIST and Lawrence Livermore National Laboratory, or I shouldn't say at Livermore, but involving people from Livermore, and IR spectroscopy from McMaster, and high magnetic field studies that we're currently carrying out at the National High Magnetic Field Lab at FSU and Los Alamos. And then I'd like to acknowledge Peter and Sasha Belowski for theoretical insight. Of course, we've talked to many theorists, but they in particular have been very helpful recently. And so a lot of names there, I'll mention the names as we proceed to the talk. And then you'll hear talks from other collaborators doing Raman spectroscopy, RICS and optical pump probe experiments, and I've underlined the people who will be speaking about that work and I'm sure other work as well that doesn't involve us. Okay, so let me start by making some remarks about uranium within true silicon just to set the stage. So I'm going to look back at some older data, and there was three important papers that kind of started this off. Work by Schwabitz, and then work by John Meinhosch's group, and then in the R group there were these three papers, and they appeared within a month of each other, and basically got the same type of results. And so I'm just going to summarize some of that work. So this is work from Paul Stewart and co-workers by Meinhosch's group. So this is the resistivity for the current along the A-axis and the C-axis. And so, for example, here you see condor-like scattering, and then a precipitous drop, and you go into the coherent fermion ground state, coherence temperature around here. And then at lower temperatures, you see anomalies that are reminiscent of charge or spin wave scattering. And here you see the magnetic susceptibility for the two directions, in particular for the easy direction. You see at high temperatures period-wise behavior with the moment that you would expect for either tri or tetravalent uranium, which is about the same value. So that's one of the things that we would like to know. And then it goes over peak, and then there's a drop here due to the long-range order that occurs. The order in the beginning was presumed to be antiferromagnetic order, which was reported by Roholm and co-workers, but the moment's only a few hundredths of a Bohr magneton, and it has this magnetic structure here with ferromagnetic planes oppositely oriented as shown in this figure. This is from our own work. This is a plot of specific heat divided by temperature versus T squared, and so you see this very striking BCS type mean field transition at 17.5 Kelvin, which we suggested could be a spin density wave or a charge density wave. And the reason for that is that you can describe this specific heat with an exponential from which you can estimate an energy gap of about 130 Kelvin. And then also, most importantly, there's a reduction of gamma when you go through this transition. So if you take the gamma that you'd estimate by linear extrapolation from high temperatures, and then take the gamma that you would measure before this becomes superconducting, then you find that this ratio is about 0.6, suggesting that about 40% of the Fermi surface is removed by whatever this is, and we suggested it was a spinor charge density wave. And so we thought that this competes with the Fermi surface for superconductivity, which also, the three groups I mentioned, occurs at low temperatures, 1.5 Kelvin. Effective mass is about 25 times the electron mass estimated from specific heat. The entropy is much too large for antiferromagnetism with this small moment, which gave rise to the suggestion that, well, I guess the exclamation that that isn't the order that's going on. And so since we don't know what it is, the term hidden order was coined. And so as I said, this order parameter, even though a lot of progress has been made, has not been definitively identified after 3 decades of research. This is work by Emitska for neutron scattering, neutron diffraction, and this is magnetic moment intensity versus temperature at various pressures between atmospheric pressure 2.8 GPa. And basically what happens here is you start out with this very small moment, and then it increases quite a bit, but then jumps up suddenly when you reach about 1.5 GPa, where it has the value of about 0.4 magnetons. And this appears to be an average moment that you measure, because when you look at silicon-29 NMR, work by Matsuda and co-workers, you find that at atmospheric pressure there's a large signal due to the paramagnetism, very small signal due to the antiferromagnetism that's responsible for this small moment. And then as you apply pressure, the antiferromagnetic contribution increases at the expense of the paramagnetic contribution. Then when you reach 15 kilobars or 1.5 GPa, it's all antiferromagnetic. So there's certain things that you can say about the hidden order phase that are known from these experiments that I've shown you. And one is that there's an energy gap of about 100 Kelvin. I think there has to be itinerant character, and that's consistent with this partial gapping scenario. Obviously, there has to be local character, and that would be due to the hybridization of the localized atom conduction electron states. And so you have a very complicated, heavy fermion, heavy electron type system, like many other systems, but this one seems to be in some ways much richer. The small moment antiferromagnetic phase resides within the hidden order phase, so most people think it's extrinsic, it's caused by internal strains due to sample defects. On the other hand, some people think it could be intrinsic. Samples of widely different quality always seem to have this in a small moment. And the antiferromagnetic onset, as near as one can tell, occurs at the alcoholic hidden order transition. Okay, so this energy gap has been observed in many experiments, and I've listed just a few of them there. And then also in spectroscopic measurements like infrared spectra, tunneling spectra, spin excitation spectra, SDM, and so on. And then there's been a lot of theory. Some of the theorists who've done this work are here. It'll be interesting to hear a discussion about this. And this is, I think, just a partial list. There are a lot more theories that I know about. But anyway, that's probably most of them. But there's some very ingenious ideas that have been proposed by this university. I'm sure you'll hear much more about that. Okay, so let me say a little bit about the temperature versus pressure phase diagram, because this will be important for the system I want to discuss. And so this is some work done by Nick Butch and his collaborators on single crystals prepared in our lab when Nick Butch was student there, in fact. And so this is magnetization versus temperature at various pressures. So you start out with this very small moment, and then you see the order parameter increases. And it increases substantially when you reach about 0.8 GPa, and then above that less dramatically, but it saturates to a value of about half a bohr magneton for the uranium ion, and it has a very steep slope here, indicating that it's a first order transition. And then from these data and some other electrical transport data under pressure, one can construct this version of the temperature-pressure phase diagram. And so from our work, then you see hidden order phase in here, antiferromagnetic phases here, and then the source conductivity is down here. Now, these points are taken where the resistivity vanishes, or nearly vanishes, but the transitions are very broad, and there are fluctuations in the superconducting state that occur in this antiferromagnetic range. But the actual bulk superconductivity appears to be confined to this region and to coexist with hidden order and probably not antiferromagnetic order. And then I draw your attention to this little kink that separates the hidden order phase from the antiferromagnetic phase. Now, this is our version of the phase diagram, which was taken in helium, which is the most hydrostatic medium. And this phase diagram was observed much earlier by many people, so I don't want to give you the impression that this was the only work. There are a whole series of works done in establishing that basic phase diagram, but I think because of the pressure media that were used for neutron scattering, lower pressures were found for the phase boundary, and I think this is probably the appropriate phase boundary, the pressure for it, but the phase diagram is basically the same as the ESP. And let's see, this is the first order line transitions, first order transitions. Okay, and then of course the electronic structure is very important and one of the topics of this conference, and I'm not going to say much about it, except to say that the Fermi surface and the hidden order in large moment antiferromagnetic states are very similar. So these are the Haas frequencies plotted versus, amplitudes plotted versus frequency. This is in the antiferromagnetic phase, this is the hidden order phase. These are measurements we have the pressure, and so you can see that they're rather similar. And when you pass from the hidden order phase to the antiferromagnetic phase, you see just small changes in the Haas frequencies, and also the effective mass seems to pass smoothly through this boundary. And anyway, this strongly suggests that the lattice doubling in the large moment antiferromagnetic phase is due to ordering with this commensurate wave vector that already occurs in the hidden order phase. Okay, and I'll say more about that. All right, so now let me talk about transition metal substitutions in uranium lithium-2 in general. So we've done a lot of work on this over the years, and so this is kind of the local disposition of elements about ruthenium in the periodic table. And so you see that if you substitute manganese, technetium, and rhenium, all of which we've studied, this dopes the system with holes, and you find the suppression of hidden order and the emergence of itinerant ferromagnetism. And I'll show you the phase diagram for that in a moment. For rhodium, this dopes the system with electrons. You find the suppression of hidden order, the emergence of antiferromagnetism. And then for iron and osmium, which we've been studying in more recent years, this is an isoelectronic substitution where you might think nothing would happen. You find a transition from hidden order to large moment antiferromagnetism. That's very similar to the application of pressure. So that's what we're going to talk about primarily today. And we're currently actually exploring these cobalt and lithium substitutions. So here are two phase diagrams. This is for rhenium substitution, which we studied a lot in our lab. So you suppress hidden order. This region here is a region where you can no longer see the features that are associated with hidden order, so that we don't know whether it drops abruptly, zero here, or extends to a critical point. That's actually near what appears to be a ferromagnetic critical point. And then in this region you get some very interesting and peculiar non-fermion liquid-like characteristics. Then in the rhodium substituted system, work done in Japan, the order is suppressed. We get some antiferromagnetism here and some complex antiferromagnetism and some high temperature antiferromagnetism, apparently nothing in between, which is quite remarkable. So now let me turn to the iron substitution. So now we're going to substitute iron for ruthenium. That is going to decrease the unit cell volume, as I mentioned. And so that's shown here. This work on polycrystalline samples. This is exploratory work in the beginning, so much easier to work with polycrystals, and then single crystals come later. So this is the A lattice parameter and the C lattice parameter. You see that C doesn't change very much. A decreases, and so the unit cell volume decreases as shown here between 0 and 2 for this value of X. And then the phase diagram based upon polycrystalline material, which was actually a lot of work involved, is shown here. This is temperature versus iron concentration, and you see that okay, these red points are very small features that are spurious. They're only in the polycrystalline materials, so you can disregard them. And so what you see here is that this phase boundary looks very similar to the phase boundaries under pressure. I showed you this peak before for low pressures, and then from higher pressure that actually goes to a maximum, which is shown here. So a similar thing happens here. There's a kink that occurs at a volume that corresponds to a chemical pressure that's about the same as this pressure right here, around 1.9 GPa, and then it goes up and then to a peak. And then this is based upon resistivity, magnetization, and specific heat various points. Okay, so in the meantime, what we suggested then that perhaps it's the chemical pressure that's driving this, and this is analogous, as I mentioned, to what happens with applied pressure from the pure compound. And so we've then gone on to make single crystals in the last several years. This is shown here. This is actually for the reading substituted system. And so work done on this. Here's some neutron refraction work by Mark Danishek, who's also in our lab. Postdoc for several years, and various of our students and other people. And so this is magnetic moment versus temperature, and various values of X. 0 is actually right here. X increases this way, and so you see that the moment increases, then you hit an order phase, and then you reach a maximum value, after which it slowly decreases. And so this then shows you, based upon the magnetization, that this represents the transition from the hidden order to the large moment anti-ferromagnetic phase. And this is work on the single crystal, so we've done everything over again on single crystals that we did on polycrystals. And so these are similar to the results obtained on polycrystals, but the single crystal data are much higher quality. And you can see that this is resistivity, so you see the features associated with hidden order and the higher values of X, large moment anti-ferromagnetism. These are the derivatives of these curves that allow you to pick out the transitions more accurately. And then this is magnetization data, and the derivative of the magnetization times temperature, magnetization times temperature with respect to temperature, and that gives you features that resemble the specific heat. And then these are the actual specific heat data. So you see very sharp transitions in the hidden order phase, and then they become broader and shift to higher temperatures in the anti-ferromagnetic phase. And this is more recent data on thermal expansion. So this is for the AB plane, this is along the Z-axis, and then this is the volume thermal expansion that you can derive from these data. And you see significantly larger jumps at the paramagnetic and anti-ferromagnetic transition than at the paramagnetic and hidden order phase transition. That's one thing to notice. And then you see some additional peaks when your concentration like 0.08 and 0.1, which is close to the boundary, you actually see 2 peaks. And these we believe are associated with the transition from the paramagnetic phase to the hidden order phase as you lower the temperature, and then from the hidden order phase to the anti-ferromagnetic phase. And so this shows these data in more detail. We don't see very much in resistivity and magnetization and specific heat, but in thermal expansion you do, so you see 2 features in these 2 samples. And then if you construct phase diagrams from all of these data, again it has a kink where you go from hidden order to large moment anti-ferromagnetism, and then you see that this phase boundary is not vertical similar to what occurs under pressure. And these two samples are the ones that have other conditions. So we want to explore this further with thermal expansion and also neutron stamping. You can also analyze these data for the energy gap. So this is an expression involving electromagnetic excitations that's used by many people to analyze the resistivity. It has an exponential part associated with the energy gap. And here we assume thermoliquid because these alloys have a lot of uranium, a lot of iron in them, and a lot of scattering. And then you can do a similar thing with specific heat, as I mentioned in the beginning, and also the volume thermal expansion. And all of these measurements give you, comparable values for the energy gap within the approximations made and so on, and also features that occur as you go from the hidden order to the volume antiferromagnetic phase. And this is an analysis using the Aaron test relation where you can derive the pressure dependence of the derivative of the hidden order or antiferromagnetic transition temperature. We just call it T sub 0 here. Derivative with respect to pressure using the change in the thermal expansion and the specific heat. This would be T sub 0 here. And so there are data here shown for the pressure dependence in the AB plane and the Z-axis, and also the volume pressure dependence. So here's an AB plane, Z-axis, and then the volume pressure dependence shown here by the black points. So these all come from thermal expansion, and then the red points are actually the actual measurements of T0 with respect to pressure at the earth. You see that they all agree very well, and that there's a very large change when we go from the hidden order phase to the antiferromagnetic phase, showing that the phase boundary certainly appears to be close to 0.11 or 0.12 for this system. Okay, we've done a lot of pressure-dependent work. I mentioned some of this a moment ago. And so here are the curves of the end resistivity that you find under pressure. We've been interested in studying the kink in the phase boundary, where you go from the hidden order phase to the antiferromagnetic phase. This is for x equals 0, no iron. As you substitute iron, then iron is going to give rise to its own chemical pressure. So you'd expect this transition to occur at lower pressures, and indeed it does. And so you can now construct a three-dimensional plot of transition temperature versus applied pressure and chemical pressure generated by the iron substitutions represented by the iron concentration. And so these are just projections into this plane from the kinks that you observe. And then you can see that the hidden order phase occurs in this triangular region. And over here you have the large moment antiferromagnetism, according to these measurements. So there seems to be an additivity here. We've been doing work in high magnetic fields. This is a progress report. And this was motivated by work in pure uranium retaining to silicon to at very high fields done some time ago. But anyway, at very high fields, you see all kinds of features in the resistivity, thermal expansion, magnetization, and so on. Excuse me. And from that work, you can, or Kevin co-workers, many people work on this, you can deduce a phase diagram. And so you suppress the hidden order phase. This is a metamagnetic transition. And then there's a whole set of other quantum phases that occur near the quantum critical point associated with the hidden order phase. And that just shows it in a little bit more detail schematically. These are measurements for iron substitutions that we've been making at the National High Magnetic Field Laboratories in Tallahassee and Los Alamos. So here are the features you see up to 35 Tesla. And as you increase the field in the hidden order phase, you see the decrease of the phase boundary like this. And then in the antiferromagnetic phase, you actually see this part, this is the suppression of the antiferromagnetism, and this part that's due to the hidden order. So you can then make a three-dimensional plot on the data that we've taken so far. And so here's temperature versus X versus field. And so hidden order is suppressed this way, then you suppress antithermomagnetism, and then go into the hidden order phase and suppress that. And we're especially interested in what happens down here, because that's where you see all these other cascading quantum phases. And this is compared to some work by Aoki on the pure compound under pressure, and this is the schematic phase diagram that he prepared. So this would be pressure, since those are pressure measurements, and they're certainly consistent. Maybe running out of time here. You might. Okay, a few minutes. Okay. So let me just mention the Osmium work. This is something we don't understand very well, but it's very interesting. And so here now we're substituting osmium. And so here you can see that the A and C parameters, the volume increases. And so this would be like negative pressure, so you think that all negatives ought to go the other way. They don't. And so here is the phase boundary you find for, so osmium substitution goes this way. And here's the phase boundary. There appears to be a little kink here, so the transition from hidden order to large moment antithermomagnetism occurs somewhere in here, although it may be at lower values of concentration than for iron. And then this is the iron phase diagram I showed you. This is for polycrystalline data. Okay. So we're in the process of studying this at this point. Maybe I shouldn't, we're almost done. Let me just say that what I was going to talk about is some elastic neutron scattering work. And so basically what's happening here is that the excitations for the commensurate and incommensurate phases that you see in the pure compound under pressure also occur in this system as you vary the iron concentration. So it appears then that this also maps onto the same type of behavior that you see when you apply pressure to pure uranium, uranium-2-silicon-2. And then I was also going to mention some elastic neutron, some IR spectroscopy work by Tom Timmis and his group, where they actually measure the gap optically and see that it increases in magnitude as you go into the antithermomagnetic phase. And so it also appears to be consistent with this general picture that I tried to lay out. That's what I was going to tell you when it comes to the end. So I think it's fair to say that this compound is one of the most interesting heavy fermion compounds. I've talked about this interplay between the interactions that you can tune with these various control parameters. You get all kinds of interesting phases as you tune it through these different regimes. Single crystals are certainly been very useful in facilitating the investigation of the physics of these materials. The order parameter, the hidden order phase, has been eluding us for a long time, and so I'm hoping that research on these substituted systems may provide important information that will finally yield the identity of this area of something in the phase. So anyway, I hope this kind of sets the stage for some of the other talks in the workshop. Thank you very much.
Well, floor is open to questions.
Well, I find this all very fascinating because you can tune the whole phase diagram by just substituting iron.
Mm-hmm.
And my question is, I don't know where the bands are derived from which orbitals the bands are derived from, because I mean, normally you would expect that the iron also induces extra scattering and induces defects.
Right.
And I mean, you probably know much more than I do the work of Kivelson, who is saying it has influence on the Malik order, or Oleg Sushiko on the antiferromagnetic order rates. To which extent can you disentangle the effect of iron defects and iron substitution and pressure?
When you raise a good point, I mean, these substitution experiments, the big drawback of them is that you introduce all this scattering, And so in these kinds of materials, you can't, look at this pneumatic behavior. So that's kind of ruled out. But I guess I would say that I don't think the pneumaticity is driving the physics. So I think these experiments kind of suggest to me anyway that there are other interactions driving the physics, and the pneumaticity that's observed in the very the samples with very high residual resistivity ratio, that's kind of a different regime. And then of course, when you talk about the electronic structure, then obviously it's going to be more complicated than what you would be dealing with in a pure compound under pressure. But I think it's remarkable that this kind of holds together to the extent that it does. And insofar as that's true, it does allow you to do experiments at ambient pressure that you couldn't do under pressure with certain techniques like SDM and so on.
I have a question about the iron versus ocean substitution. You said that one is positive pressure, one is negative pressure.
Yes.
What happens with the anisotropy? What happens
Oh,
with the CO failure ratio?
Well, that's an interesting point. And I was going to mention that. But the CO or A ratio change is the same in both compounds. So if that's what's important, then the behavior is uniform.
These are very electron rich. Is there any sense of whether iron or osmium might be squeezing more electrons onto uranium sites or taking more or accepting more from?
That's an interesting question. I don't know.
What's the difference about this antiferromagnetic phase of rhodium substitution? Is this any different?
I think there are differences. I haven't really looked into that very much. I mean, we worked on all of these things in the very earliest times when we were trying to study the competition between what we thought was a density wave and superconductivity. But we didn't go to high concentrations, and then the Japanese groups, found all these interesting things at high concentrations. So I'm not sure. I can't imagine that all those antiferromagnetic phases are like the large antiferromagnetic phase that occurs under pressure or in these iron substituted systems. Maybe at the lower concentration range it is, but it seems to overlap the hidden order phase in some complicated way. And I think that would be very interesting to look at.
Well, I have a further question. You showed a phase diagram as a function of doping and magnetic field.
Yeah.
With various concentrations. So my question is, I think in the zero doped, I think the transition seems to, there was some work by Heine et al. Which said the transition changed from second order to first order.
Yeah.
Is there any of that at finite dopings?
In the iron substitute system, we've been looking for that, and there are some hints of that. There's always a problem of separating, thermal lags going up in temperature if you're sweeping temperature. And so, anyway, we're looking for that. But we're kind of at the edge of where that happens. I mean, those measurements were made in Tallahassee up to 35 Tesla. These things start to happen around there. And so now in September we have time to go to 45 Tesla in the hybrid. And so we're hoping we'll see a lot of interesting things. Maybe some things that happen. See.
Thank you. Well, if there's no further...
Just one technical question. The hidden order transition is involves 0.2 LM2 type of entropy release, right? The hidden order
Yes.
transition. How about this large moment antiferromagnetic? Is it also 0.2 or is it much larger or is it not really LM2?
I'm not sure. We've estimated that. It's large, but I don't remember the number.
It's larger than 0.2.
Yeah, I think so. Don't hold me to that. We haven't thought too much about that. But not that.
Well,
Still have the heavy further type of susceptibility.
Oh, yes, they do. Yeah. And the in-member compound is actually non-magnetic. So, but it's not as pronounced. It's going away. the coherence temperature is increasing, and the features associated with these transitions become weaker, and so it's really going out of this very interesting range at a certain point.
Well, thank you.
Thank you.